So last day we looked at something called the ratio test, and we noticed that the ratio test would allow us to show something converges if what happened? Do you remember? Yeah, so we had to do this limit calculation, the limit as n approaches to infinity of the comparison of the next term and the current term, and it had to be less than 1. Right. So now, in addition to this idea of the ratio test, we want to introduce this idea of the radius of convergence and the interval of convergence. And the radius of convergence of a power series is just the distance from the center C at which the series will converge. So if I have, let's say, C here, and I go, I don't know, 5 units away to the right and 5 units away to the left, then the radius of convergence, of course, is 5. The interval of convergence, of course, would be the range of the x values within the series will converge. So in this case, I don't know, C plus 5 and C minus 5. That would be the range of where it will converge. So I'd like us to try some examples right now, and let's see if we can find the interval of convergence and the radius of convergence for the following 4 power series. Okay? And once again, I'm going to ask you to think about using the ratio test because we've got powers and factorials. Notice for the first one here, I'll just rewrite the limit as n approaches to infinity of the an plus 1 term. So I'm going to replace everything with n plus 1. We're dividing it, or I'm going to be multiplying it by the current term, so just the reciprocal of what you see. And remember, our goal here is to make this less than 1. Let's see if we can simplify. Notice this part and this part kindly simplify to what? Well, that's just what? 2, a factor of 2. Notice the x's just simplify to an x. And if I were to take the limit, okay, as n approaches to infinity of this times n over n plus 1. Notice it's the limit of n, not x. And so if I were to apply the limit to the n over n plus 1 using the n behavior model, all we have left will just be the absolute value of 2x. Since n over n just equals to 1, 1 times 2x is 2x. And notice this has to be less than 1. And so now that just means that 2x is between negative 1 and 1. And if I divide both sides by 2, we get this. Now, remember how the ratio test said that it's guaranteed to converge if it's less than 1? What happens if it actually equals to 1? It said inconclusive. So this is why now, after we've done this, we need to do some extra work. We need to check the actual endpoints of the range, or the interval, to see if those actual values also produce a series which converge or diverge. So let's go ahead and check. Let's check x equals to negative 1/2 first. If this is the case, when I plug in negative 1/2 into my original function here, notice what series I get. I get the summation of n equals to 1 to infinity of 2 to the power n times negative 1/2 to the power n. And if you think about 2 times negative 1/2, well, that just equals to negative 1. So this is really just negative 1 to the power of n, all over n. And if you remember this is negative 1, so it's an alternating series. Okay, I can think about taking the limit of n approach to infinity of the absolute value of this series, because it always decreases. This equals to 0. So since the absolute value of the terms decrease by what test? Yeah, the alternating series test, this converges. So what we have found is that when x equals to negative 1/2, it also converges. So now let's check the other endpoint here. Let's now check x equals to 1/2. And similarly, if I were to plug that into our original equation, Notice we have the sum of n equals to 1 to infinity. 2 times 1/2 is 1. 1 to the power of n is just 1. So we have the sum of 1 over n. Notice this is my harmonic series. And I hope you remember that this is the p series where the p-value equals to 1 and therefore it diverges. So what does that mean for my answer for the interval of convergence? I'll use IOC to represent the interval of convergence. It always goes from -1/2, and I'm going to put a square bracket around that one because it's including that one. And it goes all the way to 1/2, but I'm going to put a round bracket around that part because at 1/2 it actually diverges. So that's the interval of convergence. How do I describe the radius of convergence? Well, once again, the radius is the distance from the center. In this case, the center between -1/2 and 1/2 is 0. And so therefore the radius of convergence is just equal to the value of 1/2. Alright? Okay. So that's the idea. I'd like you to try this now for number 2. And see if you can do the same thing. So go ahead, I'm going to ask you to try that, and then come back and check with me. Go ahead. Gotta do our checking now. Check, check, check. So x is -3. We get the following summation: -2 to the power n over 2 to the power n, which just equals to the sum of n equals to 0 to infinity of -1 to the power of n. I think that definitely diverges. Think about it, -1 plus 1 is -1, right? So this diverges and converges to a number. We can check also x equals to 1. 1 plus 1 is 2, so that's 2 to the power n over 2 to the n. That's the summation of just 1 to the power n. 1 plus 1 plus 1 plus 1 plus 1. I think that also diverges. I guess I should have named a test. I'll use the nth term test here. You could have used the geometric series test as well. Same thing with this one here, nth term test or geo series tests. Both work. Anyway, so there's your answer here. Done. Okay. Our interval of convergence then, I will say, goes from -3 to 1, and our radius in this case is 2. By the way, for those of you who did all this work and said, Mr. Lee, if we look back at our original function, couldn't we have done something like this and just written that as the summation of n equals to 0 to infinity of x plus 1 over 2 to the power n? And I'd say, you bet you can. And if you said, hey, isn't this a geometric series? I say, yes, you are right. Hey, isn't the radius here equal to x plus 1 over 2? And I'd be like, yeah. So, couldn't we just do x plus 1 over 2, the absolute value less than 1, because that's what the geometric series says? I'm like, yeah. And couldn't you have just done this then? And then, couldn't we have just solved for x and not worry about the endpoints? And I'd be like, yeah. So, be aware. But at least it shows you that the two methods do still give you the correct answer. And the same answer. Okay. So, let's move on to number 3 and then number 4. Okay, go ahead and take a look at number 3 here. Notice in this case we got a factorial, so definitely ratio test stuff is where you need to go. let's quickly set up the ratio, or the limit, sorry, of the ratio. So it's n plus 1 factorial, x to the power n plus 1, all over n factorial, x to the power n, and this is less than 1. Once again, let's go ahead and simplify. And if I simplify, notice I'll get the limit of n approach to infinity still. N plus 1 factorial divided by n plus 1, n factorial is just n plus 1. And then notice this part, x to the power n plus 1 and x to the power n, that just gives us x to the power of 1. And this is less than 1. Okay. Now, notice in this case, n goes to infinity, so you would think that it always diverges. True, except for what? And what shouldn't we say? I say note. When x equals to 0, this converges. Because 0 times whatever is still 0. So therefore, the interval of convergence, well, there is nothing. It's just actually one value, this x equals 0, and the radius, in this case, equals to 0. Okay? Special case, special case, special case. Alright, so I'll leave you number 4. Go ahead and see if you can finish this one off yourself too. It's the same setup, same kind of stuff. Once again, negative 1 to the power n, don't need to worry about that because I have the absolute value. So just take a look at the x and replace n with n plus 1, so that's 2n plus 2, right? Just a note, that's what I just did there. Divide by same thing in the bottom, so that's 2n plus 2 factorial times 2n factorial, x to the power 2n. Less than 1. Simplify. I think you get x squared on the top, and you get a factor of 2n plus 2 on the bottom, and also 2n plus 1 as I simplify the factorials. Notice in this case I'm asking you to approach infinity, so I've got n's only in the denominator, infinities in the denominator. That just means that this whole expression here must equal to x squared divided by infinity, which really just equals to 0, and 0 is always less than 1, so your interval of convergence is actually all possible values, so that would be anything between negative infinity and infinity, and your radius of convergence is actually infinity. Okay? Just a quick note here. In the last unit, we found intervals of convergence for geometric series, right? But we didn't really check the endpoints because geometric series diverge when the r value equals to 1. We knew that, okay? So this is kind of like example number 2, when we did number 2. However, the ratio test was inconclusive when the ratio was 1. And that's why, in example number 1, I had to go and actually test what happens at each of the endpoints of the convergence parts, because that, of course, is where the ratio was equal to 1. Okay? Alright, everybody. You're ready to do some questions now.